Hello, good morning, everyone. All right, 6:30 in the morning now. Started this project, days ago, but 5:30 started putting it together a little bit. I'm not going to be able to make it all in this one video. Let me see if I can look at some notes I wrote for you, and then you guys can remind me that you didn't say it or you forgot, you missed it. So I say deck lifting tells a deck lifting. Oh, right. Yeah, I didn't even get that in this here. Where they lift the deck with the cranes. That's going to tell how the supports react. I'm going to be kind of excited here because I don't want to get this data out there for you. Excited meaning I'm going to sometimes talk fast. All right, so because I know I ramble, so I might try to do this with less rambling and less riddles. So the deck lifting, I don't want to lose this page. I want you to think of the cantilever and how if you were going to lift it with a crane, for example. Let's just see the rebar here. This is going to be rebar. This will be the pad, the concrete pad. And let's put the rebar at the top there. Now, if you lift here in the middle, the steel will help this from flipping over. The steel will hold it at the top. And a hook here, let's call it a hook like that, just a little hook like that. Punched hole through. They actually punch it all the way through and get the back side of there. You can see how if you pull it from the middle, it would want to do this, right? So and I like the arch there actually. So this steel at the top would stop that from deflecting down. If I were to put it down here, that when they lift here, the concrete would break apart here, and then the concrete would march this way. So looking at the removal of the and I probably will forget to bring it up for you. Looking at the removal of that one round piece of cantilever slab that I've shown you a few times, notice how flat it is when they moved it from a single point in the middle. That indicates that steel was pretty stable in there, the entire pad area. Take note when they went to move the one video where I show them throwing away steel and all that. They have two lifting points. They have one there and one opposite each other. I'm doing it like sort of an angle here. And when they cut out the slab, out, they around the punched area, around that column, they not only threw away the evidence, if you will, but they oh, that's right, it goes all the way through. Sorry. They allowed the slab to arch the way they did it, and that created a lot of that compressive zone in the middle where the guy was able to grab a lot of that material and just start tossing it. Yet the deck went down opposite of that. They didn't stabilize. They didn't have the skill set to remove it without causing damage to it, without causing deflection damage from lifting. It tells us that we saw the top steel. They were grabbing it and tossing it. The bottom steel might not have been there where, I'm speculating now because I did not get to see the sample. And it could have been fractured there upon that line where it would have bent there no matter what. Save, don't save. I have a drawing here we're going to get to. Now I want to, let's see if I can press cancel on that. So I did my drawing, and then just now, a few minutes ago, I made it this far into the Don Lehman supercomputer report. I wanted to see if my biases would match up with the supercomputer. This would be my bias, what I'm showing here. I'll get to it in a minute. Let me look at my notes again. Okay. So Don Lehman says it started at the wall, plus they said the gym. So they got two things they said. One, it started at the wall. One, they said at a gym. Now I'm going to try to be sort of nice here. She's out of her league. Apparently, they're also, if you do this, I wanted to find the article, and now it's calling Don Lehman a reporter. MiamiHerald.com, reporter, Don E. Lehman, reporter, January 12th. I was trying to find this article when that came up. The Herald built a computer model to explore how Surfside Tower fell. The Herald built a computer model. I thought they built it through Washington University, Dawn Lehman and her assistant, as we understand, right? So their computer model has a bias of her removing steel. All right, let me remove steel for you. And I've told you this before, and I'll never release the name. Don't even bother trying to get anything from it, because I'll tell you I don't remember the name or the information. Can't find it. But there was an engineer on the site that really contacted me, kept really pushing me that there's no steel back there on the back wall. That's sort of what the article says here. Dawn Lehman in the position is that. The engineer said they were going to send me photographs of the steel missing. I have not received the photographs, but that person still insists that the steel is missing on that back wall. With that said, I know that you said you're going to send photographs. I should throw you out with the bathwater now. But the photographs could be another reason why they're not being sent. I have speculated on that, but considering if that's true, I go with that. I go, okay, let me go with it. But everything I look over there, all the photographs I dive into, I keep I'm seeing cone failures in the walls, indicating to me that there's rebar in there. I do a lot of rebar pull-out tests, and that indicates that it has such a good anchorage that when it pulls out, it makes the concrete fail that's in the wall. Plus, there were multiple reactions there. I showed you that in one of the videos with the cardboard box against some steel, and then I showed you it with wood against the steel. Just go back in my videos, and you'll see it. It's only back maybe 5 or 6 videos. And you'll see the reaction I'm referencing to, where force multiplier is created on the tension side of the deck when it's failing. It's a force multiplier handed off to the compressive side of the deck. Yeah, I said that. Look at the final video, and you know what? I'll link it down below, but you got to remind me if I don't link it. I'm putting a link. Let me write this down here. Link video of ×2 of force multiplier for you. Now, I might forget that because I do things like I write my own notes, and sometimes I don't understand it. I put FM. I'll look at that note and be like, FM, what the hell is FM? I remember at the time I wrote it, I knew it meant force multiplier and put the video up. Look, I do my own shorthand and forget it. Forget what the hell it is. How many of you guys do that? So M means my M over here. Okay, I'm trying to remember what I put this in last night, and I just did M for multiply, right? It's existing column, but I had a reason why I chose M. All right, now over here is this computer. This is with them removing steel, and to remove steel, corrosion added, they get the deflection here. If they don't remove the steel, they don't get that. They don't get it without corrosion added. If they don't add corrosion, they don't get this. I work on this with the intent of no corrosion added, just the spans and how they're connected, and how they're theoretically connected. Although the images don't appear to support that. Corrosion added again. So with their corrosion added, I get the deflection here without corrosion added, and it's over here. We'll get to it. This is where the gym is where the supercomputer just crossed the line, literally, the plane of the building into the building, and this is where the better anchorage is, and this is where the supercomputer picked on it. So I would argue that Dawn Lehman and her student, her PhD student, going for their doctorates, they did some extrapolation and adding this was an error. Maybe they put their bias in there when they saw the building go down of phone calls, and they decided that we have to put some weakness over there somehow. They don't explain why, besides somehow that this is not anchored over here, and it's got the beam detail, and this is 1'6", and I've got so many videos I want to do, but you guys don't like the breaking up of the video, so it makes it longer. This initially was going to be a 2.6 foot beam, if you will, from column to wall. When they raised the deck, that reduced that beam to 1'6", but remember, it's going into a wall. It's got a shear wall that we know didn't go down, so this is pretty darn stable, and the distance and the loading of it is pretty stable. If you think about, here's a column here, it's got the forces when it's pulling down or get multiple chances to be ripped up by the interference of columns, if you will, like a perforation. Like this would be a perforation. It's a little bit staggered, but you can imagine the closer they are, the more it want to perforate it, if you will. These are amazing how they went down, and I have a story of that. But let me look at my notes again. So I have multiple failure paths. One starting here, okay, at this corner here, and that's with that crack. I have one starting, let me move this over here. I have one starting obviously here where I talk about the triangular ray, right here. I have it starting at the butterfly, this deflection. I have it starting at a fracture here and a fracture here. This is a control joint rather, and it would break away. I have it starting over here at the planter boxes, from the car loading behind it, and then the loading from this point to the wall, and then the planter blocks at the outside of it would be the beginning point. I have it starting, look at my notes here. They call them go points. I can get all the reactions from these points. The K, L, and M. So K, L, and M. So I think maybe this is M. Yeah, okay, so this would be K, and that's L. And let's delete it. These are existing. And M, I believe this is M here, 6-inch offset on M. And I have it starting here. This is based on the core sample, where this could just fall away. Now I'm going to give you a couple more things to support that, but I don't have it destroying a column. Now I do leave open nefarious reasons. I still have nefarious, the person that says they came in drunk and did that. We don't have a car there, so no car. Suicide, we found no blood. I saw no splattered blood, down there when it got down to that pad. That pad was still there when they still allowed some flyovers. So I actually look for, am I going to see some squirt? No. All right, let me read my notes. I have a KLM at planter, construction joint, parking area and corner of lobby, back wall by cars, and I put, at planter box and bias against, but at approximately 4 foot from wall on pool deck. Okay, right, 4 foot from wall on pool deck where it sticks out. I have it there as a deflection moment that starts pulling it down. So I have a weird way of visualizing. I can actually put myself like a 3D model in the deck, and I can, in this case, imagine a deck if we were walking on the deck. Now imagine if you can just make yourself a 3D model of yourself and just put your head down, even with the deck, so your feet are below the deck, and now you can turn your body around and look. And I have the ability to do that, and I can turn and look. And it's weird, right? Because you don't want to get too crazy about it, and you don't want to make your brain think too crazy. But turn around and start using your finger. Of course, you're reaching through the deck, and it comes like this elbow thing, only reaching through because you can't see through the deck. You actually go that far in your brain, if you will. I'm going to start pushing on the deck. And then I look at reactions, and I see the building in the background. And I think of the steel, how it would be reacting with this point loading. And then I have to come up with why it would be a point load there. And I'm like, no, it wouldn't be a point load. It would have to be a span load, a load that's the entire span. So then I say, okay, so this would be like a knife. Then I turn my hand to like a knife mode and start pushing down. And I'm like, where would it resist if I put a knife mode of my hand here? And I'm like, well, it would meet this first column area. So it would want to pull around here. So it would never make it to the wall. I'm like, It would first start pulling this down, and then it would make it out to here. Then I go to the wall, and I'm like, I start pushing on it, and I'm like, wow. When I try to push 4 foot from the wall with my knife hand, I'm like, I don't have the load reacting there. It would be from there. It's got like a bit of a cantilever action of steel, so off that wall. So I'm like, it's pretty rigid over there when I go to use my knife hand and my visualization of steel. And I said, wow, and I'm out here. I'm like, yeah, I would start pushing on there, but I can't. My hand starts reducing in pressure in my mind because it's like, nope, you can't apply pressure there. There's nothing to cause that. So then I come over here and go knife hand again. I'm like, oh, you can apply pressure here. You have the boxes. You have a concealed maybe deterioration behind the boxes at the steel line, the concrete there. you have cars coming in loading, so that becomes a bias. That point over here is a starting point, but not over here. This will be my last. This will be my. I wrote a note on that. This would be did not see that coming point. I put a quote there so you guys would know if it comes here. I didn't see it coming. If it's over here, besides missing steel, that would be the lady that the person that contacted me. So if this starts 4 foot off the wall here, even though I went through it, didn't see it coming because I have it. If I'm going to choose between this one starting or this one starting with the loads over here, there's no way I'm choosing out here to pull deck. Not no way. I mean, I need more data, but I'm not picking it because this is these beams are pretty much these columns back to the wall created a triangle array that's acceptable per the loading on this side. On this side, these are dynamic. I call them hydraulic jackhammering effects. I have a reason why there. Nobody calls me out on it, so oh well. So I'm going to stick with that. But these loads are variable. They change. They've been changing over the years. So I really like back here as a starting point. All right. So I like this one because of the huge distance. Now we have a bias of the crack exposed, but without that, I like this one. Before I did that, I posted this. Oh, incidentally, this is an error. Remember I had posted this months ago. So in my other room there and on the board, you saw it. So this is not 10%. This is 10 degrees. My brain just 10%, not degrees. So it's not percentage if you evaluate this. Over here we have the crack coming off here, and why I like this as a starting point is, one, we have core samples that show it. I like this as the same thing, core samples that show it, because we're losing, it's identified as not being supported because of the cracks in the core sample. And remember, I do a lot of rebar test, pull-out test, and these are there's nothing to pull out. You can just grab it with your hand like the initial driver did when he just grabbed it and threw it away. All right, so looking back here, these offsets. All right, what do I have here? So these are all movable. So that means, why did I choose them? It means existing, but I chose them. I can't pause. Sorry, someone's trying to get my attention. So this is my critical shear, these boxes that I created around, like each one of the M's. The M's would be existing, if you will. So these are the critical shears around each one of these. And so there was my shorthand that I can't remember myself. Get that box back. Where did it belong? Where did I take it from? Over here. So these are the critical shears. Now they do not take on. Let's see my notes here. Critical shear is designed does not translate to 100% down the column, meaning if you make it here, it does not mean you're going to make it 100% of the load down the column. It gives us stiffness, a larger area around the shear heads, around the columns, to help it so you reduce the idea of shearing. Okay, get rid of this one, M. And here's M here, so I guess I can put a box around that one. Oh no, it's the pool over here, the hot tub. So that's going to have its own little build-up. Let's put that back. If you notice, I'm taking a little bit of liberty. This is not the scale, but imagine if this is the stiffness. This is the and this is the. Okay, so each one of these X's. This is where I say the steel that's going across should have been supported. And does it make it? And here's the cross steel this way. So here's the deck area here. And let's see if we can just use this one. So here's the huge deck area here. See the zone? Well, here's the steel that was off of this critical shear head goes over to, well, it airballs. It doesn't go to a critical shear head. This would be the airball here. It translates to grabbing into a just typical steel going across these column heads, and that would be probably two pieces. I'm going to get to the two pieces real fast. This would be this plane. This is just showing the plane. I'm taking liberty here because this is an 8-inch offset right from here to here, and I'm going to let the 8-inch slide because it's about by 2 degrees. Oh, incidentally, this one This is a weird one. This is the one where I called out some degrees, 13 degrees here. Oh no, this one I called out 20 degrees. My gosh, this thing can be more than 20 degrees. It depends where I pick it up from again. So if this was supposed to be the column point, well then we're back to this huge offset and this direction too. It's two directional loading. Now, ACI 1979 current day, they allow you, they tell you multiple bays to use, but 2 bays. And if you're going to use like a decking material, sometimes it's 3 bays. I don't think of it that way. I think of it as until you get to the control joint, they're connected. I don't have that you can just, engineer this to use 2 bays or even a 3 bays. As long as they're connected, they're going to interact at each other. I'm not one to do that. I don't like halving either. Yes, it's how you calculate, but I don't like halving. I don't believe in that. I think we're just, in spite of our stupidity, I think we're getting away with it using this half formula. Because you can't cut away it's half of it and say it goes back here. It's not the way it works. It just doesn't do that in real life. I can't come up to the half of it and go, this load transfers back here. So I can put, 300 pounds on it. Well, go put 300, half it, cut it out with a real chainsaw or whatever, and then put 300 pounds on the end. Now see what you have. You got a cantilever effect, don't you? It doesn't work. You need it to be reacting together. And it's just old school defective thinking. Back to, this was defective thinking. Clearly allowing the architect to sign off on the work, and ACI allows that. So who's at fault here? Shouldn't ACI be paying? If these people follow the playbook, which they did, and Champlain Towers allowed the ACI, and ACI allows the architect to 79 to do his inspections, then isn't ACI at fault here too? They're the ones that chose the guardian of the inspector to be the fox to guard the hen house. This L shape, this means on this side that's open is supported, that it's probably okay. See, the column to column. In this case, it is the steel was going that way, but it's in line, so pretty much in line. Here's 6-inch offset on this one to this one, and let's move that over. So, but here is the steel from this column here. Let's see the column head. It goes all the way across. There is no column there, so let's go ahead and put multiple of these guys on to show you that there's vectors there. Let's get rid of it. It goes all the way across over to here. It misses this shear head here, so it didn't even clip it in. It would create a torque action anyway, right? And there's the cars. So there is steel going across here, but it would start grabbing on the shear head. The steel that's going across it, the deflection would want to pull down on it more so, especially it's 2-directional. See, I can move this up for you to help you visualize. The steel's going that way also. And so it's pulling as the cars pull in. Here's the planer boxes here too. As they pull in, the stresses want to pull on this way, that L shape that I have here. This L shape on this side of it. This is a triangle array, pretty much okay. So I don't have the L on it. Let's remove the L now. And let's put this box back down there. All right, so now let's slide this down. And you can see that the other one should have been right here. They even identify how much where it should be, because they talk about the offset. It's offset of what? Well, it's offset of where it should be. So it should be here at 6 foot. This one is offset at 9 feet. This is offset of what? It's offset of where the column should be. Way over here. And so I put the column where they belong, right here. That means that's where the forces were originally. They didn't change the forces. They didn't add a diagonal steel, as I put up here, where I say the steel does not run in the angle of offset, resulting in a torque loading right here in my notes here. They don't change this pattern of the steel. No, the steel's still running cross-sectional. Now this is where I think each column should be. A column should be there, column there, column there. And it turns out that's what they say also. I base it on this one, trying to maintain a triangle array. But parking is an issue. So let me move this X here, and let's get rid of that. So this is where I think a column should be. Let's move this X and move this one. This is where I think a column should be. Why did I choose this one? Okay, because there's a column back here. All right, and this is where there's a column here. So I put a column opposite. This one's the spans from here to here are about equal to the span from here to here. So not necessarily, this is an extra column up there. So we'll put that over there and reserve it. So that would work. And then based on how these are working. But the spans now are increased from here to here. It's a much greater span than from here to here. These spans are stable. We know that because we look back into the building structure where the car is existing, and they're stable. They didn't go down. It didn't continue. Well, it didn't continue because they created a control joint there via their anchorage, and the failure because of the core sample gave a shear plane. And the crack here, and then this one over here, this dot, 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 dot. That's that landing where the gym is and where the planter box is. And right back here is where they claimed the Miami Herald and Don Lehman and the University of Washington claimed that it started at the right there inside the gym, which is inside the building. Yeah. Okay. So this is a control joint. Outside the control joint, if you guys, I showed you in one video only so far, I think, there's another fracture. So to me, it might have, this might have been a cantilever before when this deck started going down. It got over to here and it resisted for a moment before it snatched it, and it created a fracture here. And then it snatched it out of the control joint and it dropped it down on the ground. And if you look on the flyover images, you'll see this fracture right here going across. Specifically, look by the column that's over here with a chair sliding down by it. I don't need this, so I'm going to move it off. I don't need this because I'm going to move it off. So as we start revealing and working our way backwards, I'm going to put this X here. This is where I believe a column should be. That's where they believe it also, it turns out. Let me get rid of this one in the background. Let's get rid of this one. They had a different reason that I was working them last night. So this is where I believe a column should be in here. And then, of course, we have parking issues, so they had to fix them. But this is not where it was. Delete. So it continues over to here, and it goes from column to column. Now it's out of the critical shear zone. There's that L shape. Okay. So there's my L shape. This means what I'm thinking. This helps me remind me to tell you guys it's grabbing from. Great. Okay, I'll put it around there. I'm taking liberty on the sizing scale. So but it doesn't make it over to there. It's 6 foot offset. Those aren't 6 foot critical shear zones. Let's see, 6 foot. So that would be, yeah, they're not. So it makes it into the steel. So this loading makes it in here, which then pulls down on here. But I would extrapolate that the forces are greater in the middle here, and this makes it into the critical shear zone, these two steel here. So I would say that this one is being pulled on more so because this is only making it into cross steel, but it happens to be hitting the cross steel, maybe two pieces, two rabbit ears I call them there. But it also has to support the deck from this side also. So it's doing double time. It's doing double duty there. Let's run our butterfly down here, my bias butterfly. And this should be our deflection, our knife, if you will, a hand there pushing down. And now as I look from here, head in the deck, looking right above the deck there, and I look this direction, I put the knife hand on it. I start pulling down on these, and I can only pull down so much before it starts pulling. Remember I showed you guys the two cardboard boxes? I did it from my porch, and I showed two UPS boxes or something like that, FedEx boxes, and I put them over a head of a column, and I did opposite sides of pulling left down and right down. And so if I pull down this side, it actually will strain this side, the steel will, or this side, whichever one the steel decides to go with. I'll show you that in a moment. And it will then have the ability to fall away from here, fall away from. Not fall away from. It won't jackknife it up. As this goes down, this won't jackknife that. It will actually pull it, and this will lose its strength across the column head, and it'll start sagging from here to here. This is my little indicating, saying that steel is there. Okay, so there's your steel going across, and that's where it's loading. Here's our steel going across, and this is where it's loading. There's no critical shear zone around it. There's no like, oh, we did that, now let's stiffen this up, and then it'll tie into that steel better. We'll make this stiff, a rigid joint, a nodal area. Okay, so think of them as nodal areas. So this nodal area is weak. This nodal area is weak. This nodal area here is weak. Nodal area here going across where it ties there. Zip. This is a miss for this one here. This is a miss also. Nodal area defective. So now I look at all these nodal areas, and I start saying, wow, well, this is a good nodal area. They intersect there. The deck going across is still going here. Well, it's intersecting at a nodal area that's not in a good, critical shear area. Slash tag. Oh, that's one of my new words. Slash tag. I like that. Let me write that down. Something I can have fun with. So they don't have stiffness, if you will. So the deflection there could start here. Okay, it could start here, but they're pretty close. So it's pretty close over there. So this would be the weaker one. This would be a little more stiff over here than here. This would have more deflection on this side. That's now biased now, because that's where the planer box is. This one's between these two. Closer to this one, it's getting near midline, but it's a little more stiff than this side, so I'll pick on this side. So we've got stresses in this direction coming off of this one. Stresses in this more so on this one from this side. Because remember, don't forget the cantilever effect, or the pry bar effect, I like to call it also. This puts the load further out, which is strained. This would be a long cantilever, and it's a three-sided triangle-ish cantilever, if you will, a pad that I'm putting point loading here on this pad and being resisted by the steel in multiple directions. But I still visualize it as a little torque action. But as I try to push down, I get resistance from this one because it's so close, so it's going to resist more. So this would be stiffer here, not as stiff down here. So then I'm triangulating without cars yet. I come this way, right? So do that. Triangulating, looking at here, I pick on this one. Well, they already made that a home run. That was easy. That's just about where I would pick on it. That it starts torquing from here. That line's already carrying over here, so biasly so that carries there. All right, so these are the patterns. I got my car problem back here because I can pick on that one. All right, that was my line. I can pick on that one. I've got existing cracks we talked about back here, so I can pick on that crack going that direction. So I have sagging here. I pick sagging here because the fracture here, it goes like that roughly. Where's my column? Am I off by? Oh, I gotta move this. Yeah, there's the column. So I have the sagging there to create that lateral fracture, something like that. That's too straight, but there's a column there. I've got a core sample here that indicates that there's no real connection there. I'll back that up in a second. Yeah, I'm not going to be able to do this in one video. You got to absorb this anyway. So here's a nodal point. There should be a nodal point here. There's the offset. There's my butterfly because of mid-span. So I use the mid-span as the heaviest part of the load, where it's loading the most. And let's jump into the photographs real quick. Oh, got to move this out of the way. Right, so that's that. And then over, same, over. Oh, okay, so here's the report from Morbido about the waterproofing. And let me move that down there. And you need to look no further than than his report. Now I posted this. I'll give you the dates if I can. Looks like I gotta close it. He's picking on that, but in reality he could pick on long or whatever. Now I put this one out a long time ago on the video. L-bent rebar 90 degrees as plans call for. But take note, again, I do a lot of rebar pull-out tests. This looks like somebody smashed it with a hammer to be able to, the concrete, to be able to get that steel not to be bent like that. So it tells me it was degraded that far down. This is, delamination hanging over the one piece of rebar there. Looks like a wire mesh, metal wire mesh. This one looks like it was hooked, and then when it went down, it just barely held on and bent itself back up, backwards like that. See the total absence of concrete between these, and the spacing looks pretty good up here also. So this is where they made a joint, I think, and that's why you see it looks like 90s. If I were to bend this down and maybe turn it, they may look like they're in plane with us, but they might be turned away from us. Let's see. So I'll get rid of that. So there's where'd you go? So here's our failed column, and I did one showing that using a string line on each side there, and I went across each one of these columns, and they look like they're in plane with each other height-wise. Now, if you guys want to know the date on these, how do I do that again? So you can see that I didn't just add these and trying to come in for the win, if you will. Oh, there it is. I saw it now. It's got a date right here, 2021. Right. So how about that? That's good enough. That just says 2021. We're in 2022, so that's good enough. So this is where I'm saying if they had the BMA there, that would have been a big deal. Oh, this is the top view image. There's the fracture that we're talking about there. The fracture that comes all the way across. It comes all the way across, makes it over here to the head of this one. And there's the planter box turned over. PMA below deck. Is that right? Yeah, well. This is the other parking garage. Oh, I know what I want to do. I want to show you that steel. Yeah, so I did this couple of times. You see this took a lot of work, but this shows all the steel, and I was like, you know what, you guys aren't ready for that. It would drive you crazy. It's sort of what I'm doing now with the cheaper version of it, but this steel is scaled, and it's scaled in both directions, this one and this one. And when I did it, I started zoning over here, which happens to be our car parking area again. And yeah, so here we go again. Oh, this is the rough estimate of where it is. So if you try to read that I nailed something there, it's just rough estimate. They're not, it's where I think the columns might be. They're not home. There's a lot of them are home runs, but he helped me find K. And I found K, which is right here. That's K at the wall. And you can see the rub off there. Here's the planter box. It was in front of K, so that's in front of the apartment 111. Yep. So there's K, and there's K, and that's K. So it shows you that you can eliminate K as being these guys from being crushed, if you will, or buckled over, as many people want to kill a column to make this happen. I try to kill a column differently, though. I try to get it through subsidence, that the cycle loading of the water below made the whole pier, the cap, and the 3 pressure-induced pier columns, piers, also sink, if you will, and then it create a pull-down effect of the deck. And then using my 3D, my brain there, I look at the pull-down effect, and I'm like, oh, that would work. I would just need, and it would work in multiple positions. I would just need to get the deflection, a crack in the basement on the floor. where the car's parked, and I couldn't nobody revealed that. And I would need to get to the when they were doing the testing, the NIST with their pressure testing of the piers, loading them. I would also need to see that it just drove down like nothing, but that wasn't to be materialized. Nobody's come forward with anything like that. Back that off. All right, so this is clearly leading over, so we don't have our start point right there. So that's sort of elimination. Let me find somewhere else. I want to find you something. Oh, I know what I'm going to find you, the shear head. Yeah, I want to get you the heads, and then I'm going to end this video with that, and then I'll come back for you. Oh, it's in a video. Here we go. Rebar pull-out test. All right, so this steel is too heavy to be inside that layer for the topping layer. All right, I don't think they used that. Looking over here, I don't think they used a wire mesh. Looking at this steel, we see my rabbit ears right here, my two antennae, my roach antennas I call them. This tells you that this steel was probably the top steel of the structural slab, and that with this deck went down, the deflection being over here, it just stripped away from this. Now let me tell you, doing rebar pull-out test, if rebar is engaged, it will snap. You don't get to pull it out of the concrete unless you've got a weak bond cement mortar, a weak bond, and we know that through core samples there's plenty of them. Don't get too excited yet, because when we look at their NIST, my NIST video of them destroying the evidence, I say, look at that concrete there. You'll see that concrete is stable as hell. This is him winking about their investigation. If you remember, you can find the video. You come here, 3014, do it frame by frame. We're doing it, and that's the winky, I call him, right? So you wink. Yeah, this is the video here. Champlain Towers Smoking Gun Engineer. This is Tong Lee at 2150. He's the one that should be getting a lot of slack too. You know, his company. I don't know about the statute of limitations they're talking about, but he should be getting thrown on the bus also for not catching some things, because he loaded it with this. He added the extra loading. So the ears here tells you that this side of the deck was was engaged, held the rebar, and this side to a huge tune. If I could put this back up here, this rebar might have went all the way over to here. The lap might have went over, 4 or 5 tiles. I'm scaling tiles at 1 foot square, and this might be, once you lift it back up, 4 or 5 feet minimum, might be back to here. But it when it went down, it just stripped it right out the top of it. Again, if you look in this video, you'll see that don't look at what they're lifting up, but look where they cut out. Look what's remaining. I was looking for a degraded core sample, if you will, because I have a profile of the deck at that point. You can look at it too. You will not see that that degradation. You will not see. You'll see. Where's my next video? So I can sort of prove it to you a little bit. Wow, they don't recommend a single one of my videos over here, do they? This one here. Here we go. I'm like on my own channel. Yeah, that's a nice one. I like that one for explanation for you guys. I'm gonna end this video. We'll get to that. Maybe we'll remember. Let me look at my notes real quick. Okay, I'm gonna terminate this video. I'll have to do another one for you. Take care.